On October 29, 2025, something in the inner solar system flared like a blue lighthouse. The interstellar visitor, known as 3I Atlas, skimmed the sun and became roughly 5 times brighter in a matter of hours. Natural comets do not brighten like that without throwing off huge clouds of gas and dust. Telescopes searched for the missing halo and found almost nothing. A basic law had been broken in plain view. What brightened if the debris did not appear? What switched on at perihelion? The mystery starts now. Like and subscribe so you do not miss the next measurements and their meaning. Comets are often called dirty snowballs. Ice near the surface warms, turns to gas, and jets into space. Sunlight then reflects off the dust and glows in the gas itself. When a comet brightens a little, it is usually because a little more ice is venting. When a comet brightens a lot, physics demands a lot of venting. The glow and the ejected material rise together. That is, the rule carved into every astronomy textbook. 3I Atlas did not follow the rule. The brightening was confirmed by observatories around the world after the perihelion pass. Data flowed in from late October into early November. The numbers were checked and cross-checked. The increase in light was real and dramatic. Yet, imaging did not reveal the vast envelope of gas and dust that should have been there. The sky did not fill with the kind of expanding coma that a surge of activity would normally produce. The mass budget is where the paradox bites hardest. To gain that much luminosity through ordinary outgassing, the nucleus should have thrown away a significant fraction of itself. Think of a stone that burns off a shell to shine brighter. The lost shell must go somewhere. It should billow out as a detectable cloud around the comet. Astronomers pointed instruments at the predicted volume and did not find a cloud with the expected scale or density. The subtraction does not add up. Momentum adds a second layer to the problem. When gas streams away from a comet's surface, the nucleus is nudged in the opposite direction. It is a tiny rocket. The push can be measured as non-gravitational acceleration. Months before perihelion, the path of Atlas looked clean and simple under gravity alone. Around the sun, the behavior changed. Analysts began to see a shove that stayed aligned within the orbital plane rather than jittering in random directions. That is not the usual fingerprint of many small vents switching on and off as the body spins. None of this requires a leap to extraordinary causes. Strange terrain can channel jets. Dust can clump in ways that scatter light differently. Observers can miss faint structures when the sun's glare is fierce. Natural explanations exist on paper. Yet the stack grows tall. A fivefold flare without the matching halo. Hints of a steady push where chaos should reign. Dates that line up with a window when the object is hardest to see, from Earth. Each piece on its own is a story that might be solved with patience. Together they tighten the puzzle. Here is the task in front of us. Hold the excitement of a blue flare in one hand and the discipline of first principles in the other. We will test what the brightening demands in mass, what the trajectory reveals about hidden forces, and what spectra say about the substance doing the shining. By the end of this journey, the rulebook will either expand or the mystery will deepen. Either way, we win knowledge. Start with the simplest picture. A comet brightens because sunlight heats fresh ice. That ice turns into gas, and jets drag dust into space. The gas glows, the dust reflects, and both together build a halo that telescopes can map. If the glow jumps by a factor of 5, then the mass budget should jump with it. You do not get a light show for free. Somewhere there must be a bill to pay in lost material. Teams around the world ran that arithmetic in the days after the perihelion pass. Observations from late October into early November cross-checked the photometry. The surge in brightness was real. From there, the rocket analogy does the heavy lifting. When the nucleus throws mass in one direction, the remaining body is nudged in the other. To get the measured light output, the estimates point toward a mass loss on the order of 13% if the process is ordinary sublimation. Now look for the signposts that such a purge should leave behind. A thickening coma, a measurable plume structure, a debris envelope that starts dense near the nucleus and thins as it expands. Intensive searches tried to paint that picture at visible and near infrared wavelengths and found nothing of the expected scale. There were no images showing a giant cloud that matched the numbers. The void is the headline. The halo that should tell us where the mass went does not show up. Could the cloud be there but hidden by geometry? Perihelion places the comet in brutal glare. Instrument teams often aim off the limb of the sun to avoid saturation. Maybe the cloud sits where we are least able to look. That is a fair challenge. But post-perihelion, as the angle improves, a truly massive envelope should still betray itself with a measurable signature. Dust scatters sunlight, gas emits at specific lines. If the mass loss was as large as the brightness implies, at least one of those channels should light up. Another escape hatch is speed. If material is expelled at much higher velocities than thermal sublimation allows, then less mass is needed to produce the same push. Imagine a tiny amount of very fast exhaust instead of a giant fog of slow vapor. That would reduce the size of the expected cloud. Yet an ultra-fast jet does not make the observational issues go away. It would carve structure into the coma and produce time-variable features as the nucleus rotates. Those signatures are not showing up at the strength the large brightening suggests. Dust physics can help or hurt the search. If grains are larger, sunlight scatters differently, and the coma can appear surprisingly subdued. If grains are very small and tend to clump or align, the phase angle can trick the eye. These are real effects. They have saved other comet puzzles in the past. The trouble is that every knob you turn to, lower the visibility of the cloud, must still keep the dramatic increase in light. That is a tight fit. So, the paradox stands. The flare was huge. The expected fog is faint. The rocket math points toward a serious shedding of mass, while the images refuse to confirm a matching debris field. Either the mass left in a way we do not yet understand, or the brightening was powered by a mechanism that does not require a comet to steam away 13% of itself. The first option means we missed something big and diffuse. The second means we are bumping against the edges of the standard model. Before we choose a side, we will keep following the numbers. If the cloud exists, expanding shells should be detectable over time, even as the comet recedes. If the cloud does not appear, the mass budget must be balanced with another kind of engine. The next measurements are designed to decide between those paths. The first clean way to see an invisible engine is to watch the path it leaves behind. Astronomers fit an orbit to the positions of Atlas, and then study the tiny residuals that gravity alone cannot explain. Before perihelion, the fit looks ordinary. The object behaves like a cold stone in sunlight. After perihelion, something changes. A gentle but persistent shove appears in the data. Break that shove into directions and a shape emerges. One component points away from the sun along the radius line. Another runs sideways along the path of travel. Together they live neatly inside the orbital plane. The push that would lift the object out of that plane is absent. There is no vertical component that rises above or dips. Below the flat disk of planetary motion, geometry can be as eloquent as a diagram. This geometry whispers order. Strength matters too. The detected signal rises to about 3.7 standard deviations above background noise once the comet rounds the Sunday. That is not a thunderclap of certainty. It is also not a mirage that disappears when you blink. The result survives different fitting methods and a standard normalization that accounts for how solar radiation pressure changes with distance. When you scale the acceleration to the Earth-Sun distance, the pattern holds. Now compare this to how natural comet jets usually behave. Surface vents switch on as sunlight sweeps across them. The body spins. Different patches wake and sleep. The overall force jitters in direction, and strength like gusts chasing leaves. The result is a noisy fingerprint that smears across time. In Atlas, the fingerprint looks tidy instead. The directions stay roughly fixed relative to the orbit, as if one, the vector is pulling outward from the sun, and another is nudging forward or backward along the track, with little inclination to wander off the plane. There are natural ways to tidy up a messy engine. A dominant supervent could live near a latitude that faces the sun at the right season and the right spin. A deeply eroded trench could channel gas in a consistent way. A spin axis that tilts almost perpendicular to the orbital plane can keep most forces in plane. None of these require exotic ideas. They do require a stack of just right conditions, and the stack grows taller when you remember the missing cloud that ought to mirror this strong activity. There is also the question of timing. Months of quiet gave way to a sudden appearance of the shove right at perihelion when the sun was blinding direct observation from Earth. The switch-like timing could be seasonal chemistry waking up. It could be crust cracking under thermal stress. It could also be an engine that waits for the moment, when small course corrections matter most and signals are hardest to watch. These are competing stories that make different promises about what comes next. A rotating natural vent should imprint a rhythmic modulation on the acceleration as the body turns. A controlled push should keep its vectors steady despite spin, or show deliberateness in how it compensates for rotation. A natural surge should be accompanied by a measurable dose of gas and dust somewhere downrange. A cleaner propulsion would ask for less mass and leave fainter traces. The way forward is simple to state and hard to execute. Measure the push as the viewing geometry improves. Track whether the directions drift as the subsolar point marches and the spin carries terrain in and out of daylight. Look for periodic wiggles that breathe with rotation. 3 Atlas has already written the first half of this note in a steady hand. The next pages will reveal whether the pen is wind or intent. Begin with the kitchen, a table version of comet chemistry. In our solar system, iron is generally more common than nickel because of how stars forge elements and seed young systems with their ashes. Dirty snowballs usually carry generous water ice mixed with rock, organics, and a suite of carbon-bearing molecules that glow and scatter light in familiar ways. When a comet swings near the sun, that mix produces the classic look many of us have seen through binoculars. A bright head, a ghostly tail, a spectrum that reads like a well-worn recipe. 3 Atlas reads like a recipe written backward. Spectra suggest that nickel outweighs iron in a way that is strikingly unusual for small bodies that formed from typical solar system stock. The ratio of nickel to cyanide is far above what has been seen in other comets, including prior interstellar visitors. The bulk water fraction is closer to a dry rock than to a slushy snowball, hovering around 4% by mass in the estimates that observers discuss. If you strip away jargon, the message is simple. This object is lean on ice and rich in metals where we do not expect that balance. Why does iron usually lead? In stellar factories, iron tends to be produced in higher abundance than nickel. When dust and gas collapse to make planets and smaller debris, that balance carries through. Comets then preserve some of the cold chemistry from the outskirts, with water and carbon compounds acting like a signature of where they formed. Flip that balance, and you are forced to ask whether the material was processed in a harsh environment, irradiated for ages, baked and sifted, or simply born far from our familiar conditions. There is another clue that does not fit the usual template. Light scattered from 3 Atlas shows strong negative polarization across certain angles. In practice, polarization is a measure of how the electric field of light prefers to vibrate after bouncing off dust. Most comets show positive values, or only mild dips below zero, depending on geometry. A deep negative signal hints that the grains have odd textures or sizes or coatings. It is like tapping a bell and hearing a tone that says the metal is strange. Imagine the dust as a city of buildings. In most comets, the structures are a mix of sizes and shapes that scatter light in a predictable way. Now replace them with a district built from different bricks. The reflections change. Polarization swings negative where you expect a gentle rise. That does not tell us the exact blueprint, but it tells us the neighborhood is not normal. Could ordinary processes drive the mix toward more nickel and less iron, toward less water, toward unusual dust? Cosmic rays can erode or alter surfaces over millions of years in deep space. Thermal processing near previous stars could cook away volatiles. Impacts can compact and sinter grains. Each mechanism is plausible in isolation. The challenge is that all of them would need to act together with the right strengths and histories to stack into the pattern we see now. There is also the practical side of activity. If water is scarce, the conventional engine of sublimation is weaker. That should mute the classic coma driven by steam and carbon compounds, yet we saw a dramatic brightening. So what is doing the work? Metallic or mineral-rich dust can be an efficient reflector. Small changes in how grains clump can swing brightness upward without the same gas burden. These ideas soften the paradox, but they also have to explain why other comets with different dust recipes do not routinely mimic this behavior. What matters is the consistency of the clues. Nickel over iron, nickel over cyanide, a water content that leans dry, a polarization tone that sits where models do not predict it. If any one of those stood alone, we could shrug and call it a new entry in the catalogue of comet quirks. Together they push us to treat composition as part of the engine, not a sideshow. The chemistry is telling us that 3 Atlas does not merely move in odd ways. It may be built in a way that makes those motions easier to sustain without the usual clouds of steam. Orbits carry their own fingerprints. 3 Atlas rides a retrograde path that runs opposite the traffic of the planets, yet it hugs the same flat stage where the planets move. The orbital plane is aligned within a few degrees of the ecliptic, close enough that the object glides almost parallel to the grand ring of worlds instead of slicing through it at a steep angle. That combination is not impossible, only rare. When you roll the cosmic dice enough times, a tidy alignment will show up. When you roll it and also ask for retrograde, the request becomes bolder. The itinerary deepens the intrigue. The path threads within notable distances of Mars, Venus, and Jupiter. Not collision ranges, yet close enough for modelers to circle the encounters as interesting waypoints. Then comes the timing that stings. Perihelion lands during a stretch when the sun blinds most Earth-based views. If you wanted the hardest moment for our instruments, you would pick the days when the target sits right against solar glare. That is exactly when the object brightened, and when the non-gravitational push first left a measurable bruise on the trajectory fits. A fair-minded reading says this could still be random luck. Interstellar visitors pour in from directions we cannot predict. Some will happen to align with the plane, some will pass by multiple planets. Some will swing closest to the sun when Earth has the worst seat in the house. Each piece earns a small probability, none is zero. Yet the story does not ask us to accept one odd feature, it asks for a stack. A rare orientation, a chain of noteworthy passes, a viewing schedule that conveniently erases details at the critical hour. Stacked odds are still odds, but they argue for caution before we wave them away. Imagery adds a visual twist that refuses to be ignored. Earlier, observations resolved a teardrop-shaped cocoon of dust flowing from the nucleus. That is already interesting because it reflects a compact source embedded in a streaming envelope. Then a feature appears that runs straight against the rule of comet behavior, taught to every beginner. A jet points sunward. Comet jets normally blow away from heating. The dayside cooks, gas expands, dust rides the flow, and the resulting tails lean away from the star like flags in wind. This time, a spout seems to aim at the Sunday. Could that be a trick of the eye? Comet nuclei are lumpy worlds with cliffs and hollows. Material can arc around a curve and look sunward for a moment, depending on the angle. A rotating body can line up a vent so that its spray swings through the forbidden sector as we watch from a biased vantage point. Geometry can lie to us. The rescue is possible, and responsible analysis keeps it on the table. Even so, a genuine sunward jet sits high on the list of things that should not appear without special staging. The point is not to prosecute unlikely events. It is to recognize the pattern of many small unlikelies living under one roof. The alignment near the planetary plane has a non-zero chance. The chain of planetary approaches has a non-zero chance. The perfectly inconvenient timing has a non-zero chance. The strange jet has a non-zero chance. Multiply enough small numbers and you get a smaller one. That is where judgment enters. At what product of chances do we declare that coincidence has done too much heavy lifting? There is a healthy way to resolve that discomfort. Treat the pathway as a testable pressure point. If the jet is a geometry trick, the signature should change as the viewing angle shifts and as rotation turns terrain into and out of sunlight. If it is a persistent feature, it should repeat and carry a stable direction. If the alignment and timing are just luck, the next months of motion should look ordinary once the object leaves the harshest glare. If there is deliberate control behind the tidy and plane pushes, the vectors should keep their poise. 3 Atlas has taken a route that ties together numbers and images and timing in a way that strains the default story without breaking it. Whether we are watching a masterclass in coincidental geometry or the footprint of a guided traveler, the orbit will keep telling tales as it unwinds. The next chapters are already being written in the slow bend of the path, and the way any jets hold their aim. 3 weeks before 3 Atlas turned heads at the Sun, another Atlas-named object had already run the gauntlet. C-2025 K1 Atlas dove to within a few tens of millions of miles of the solar furnace. Many modelers expected it to crack, flare, and fade into a train of crumbs. Instead, it rounded the bend in one piece and began to glow with a color that felt wrong for a comet. Not icy green, not cobalt blue. A warm metallic gold poured down its tail like sunlight, hammered into ribbon. Color is chemistry turned into light. When comet gas glows green, it is often from carbon molecules that are shaken by sunlight and then shed energy at specific wavelengths. When tails look bluish, ionized carbon monoxide writes that color into the flow. Dust can redden or mute the palette depending on grain size and mix. Gold is not a standard entry in the comet catalog. Gold means that the usual carbon-bearing molecules are startlingly scarce, and that dust is doing most of the visual work in a way that shifts the tone toward a burnished sheen. Spectra from ground-based observatories back up what the eyes suggest. The lines that shout carbon are quiet. The signatures of dicarbon and cyanide and carbon monoxide sit low enough to look like afterthoughts. That turns the usual comet recipe upside down. Most icy wanderers are rich in these volatile compounds. They are part of the frozen pantry stocked in the deep cold where comets form. A comet that is poor in those ingredients behaves differently when the sun turns up the heat. There is simply less to vaporize and less gas to drag dust into billowing fans. Now, add survival to the color puzzle. C-2025 K1 skimmed the kind of thermal and tidal stresses that often shred fragile bodies. You would expect its brightness to peak near perihelion and then fall off as the small remaining supply of volatiles burned away. Yet after the swing past the sun, it settled at around magnitude 9 and held there rather than dropping like a stone. That plateau does not scream miracles. It does ask for a mechanism that keeps the dust reflective without the usual carbon-rich fog. There are workmanlike answers that do not require new physics. If the dust is composed of minerals that reflect sunlight efficiently, and if the grains are packed or shaped to scatter light in a favorable way, the object can stay photogenic longer than models tuned for typical carbon chemistry would guess. If a crust hardened, by earlier heating muffles the venting and meters the release over time, the glow can settle into a steady state. The point is not that the path is impossible. It is that the path is uncommon and it lines up with the unusual color. The timing of discovery and the naming seed a psychological trap and also a genuine pattern. The Atlas Survey Network scans for motion to protect Earth, and it tagged both objects in the same year. That is not suspicious by itself. The system is busy and successful. What raises eyebrows is that both newly found Atlas-branded comets refuse to behave like the templates in textbooks. One turns blue and bright without the giant fog that should attend such a surge. One survives a death dive and wears gold because it lacks the carbon that would normally paint its tail green or blue. When anomalies travel in pairs, the human brain knits them together. That can mislead us. Coincidences exist, yet the pair is useful even if it is a coincidence. The Golden Comet serves as a control against which to test ideas raised by the Interstellar one. If carbon depletion changes, scattering strongly, does that help explain parts of the brightness story without invoking massive gas loss? If survival near the sun owes something to structure and composition, what does that imply about how different comet families handle stress? There is also a practical gift for observers. At around magnitude 9, the Golden Survivor is accessible to dedicated amateurs with modest telescopes under dark skies. That means a wide base of images and spectra can be collected across many nights and locations. Patterns in color and morphology can be tracked as the geometry changes. That growing library of independent measurements keeps the science honest. It also tightens the weave between the two Atlas stories, because every confirmed feature in the Golden Case sharpens the questions we carry to the Interstellar case. So we keep the picture simple enough to hold in the head. One comet from our own far frontier that should have failed and did not. It wears the color of absence and holds its brightness longer than a standard forecast would predict. The other comet came from the space between stars and stacked a different set of surprises. Together, they challenge our reflexes about what comets must do. Apart, they give us two laboratories where light, chemistry, and dynamics can be read like pages in the same book. The rhythm of discovery usually has a public soundtrack. The National Aeronautics and Space Administration posts images, mission pages refresh, and scientists explain what just changed. In early October, that soundtrack went quiet as a shutdown paused normal operations. Silence is not proof of anything, yet it reshapes the stage, because questions keep piling up while the official microphone is muted. Inside that pause, a request arrived from Capitol Hill. A member of Congress asked the agency to release records and imagery connected to Atlas, framing the material as crucial for understanding visitors from beyond our system. A call was scheduled for early November rather than immediate disclosure. That delay may be ordinary scheduling. It also lengthens the shadow between a startling event and the documents that could clarify it. Another office entered the margins, the All-Domain Anomaly Resolution Office within the Department of Defense. They stated that they were monitoring reports, then assessed the object as a comet and therefore outside their lane. That logic sounds tidy on paper, yet it risks skipping the hard part. The hard part is checking whether the category fits the evidence, rather than allowing the label to carry the argument. This is where circular reasoning can creep in unnoticed. If a thing is called a comet because it looks like a comet at first glance, and then the label is used to ignore behavior that bends the rules, we are no longer testing a hypothesis. We are protecting a category. That is not a conspiracy. It is a very human habit, and science works best when it catches those habits in the act. Bureaucracy is not a villain in this story. Agencies need procedures. Shutdowns freeze those procedures. Even so, the sky does not pause for our paperwork. 3 Atlas moves on, and with it moves the window for the cleanest possible measurements. Every lost day under heavy glare is a day when a critical signature can thin out or drift beyond the reach of a given instrument. Fortunately, the universe does not require a single gatekeeper for its light. A global archipelago of amateurs and professionals keeps observing through the lull. Backyard telescopes and university domes and national facilities outside the shutdown continue to collect images and spectra. When enough independent eyes watch the same object, patterns survive the noise and the politics alike. That distributed approach carries a deeper lesson. Openness does not mean noise and rumor. It means methods that others can copy and results that others can check. Publish the way an image was calibrated. Share the code that fits an orbit and computes the residuals. Note the exposure times and the filter bands. When many teams can reproduce a feature, its reality hardens regardless of who made the first claim. The coming international campaign makes that principle concrete. The International Asteroid Warning Network has fixed dates and agreed protocols for pointing telescopes once the geometry improves. That means coordinated wavelengths, repeated scans, and cross-checks between different instruments. It means the missing cloud, if it exists, will either be seen by more than one team or will remain stubbornly absent under a brighter spotlight. In the meantime, we should be careful with stories that feel too neat. Government silence can be mundane rather than meaningful. Agency caution can be a guardrail rather than a dodge. The only fair test is the one that a stranger can repeat with the same sky, and similar tools and arrive at the same conclusion. There is also a civic dimension worth naming out loud. When the public can watch a process unfolding close to real time, trust travels farther than any press release. People are not allergic to uncertainty, they are allergic to being left out. Invite them to see how a measurement is made and where the doubts live, and the result becomes a shared artifact rather than a decree. So the path forward is double. Pressure institutions to release what they can as soon as they are able, and build an independent scaffold of observation that does not rely on a single switch being turned back on. 3 Atlas is writing a complicated sentence across the sky. It deserves readers in many languages, with many kinds of telescopes, copying the text by hand until every letter is clear. Science earns trust when it writes down what should happen next, and then stands back. The calendar already has that writing. As 3 Atlas pulls away from the sun and the glare eases, a coordinated campaign from late November through late January will turn telescopes toward it. Geometry improves. Background light drops. Instruments find their stride. This is the window where a hazy mystery becomes a measurable thing. If the brightening was powered by ordinary sublimation, a large expanding cloud must exist. Dust should scatter sunlight in a smooth profile that balloons with time. Gas should glow at known fingerprints of water, and the fragments it leaves when sunlight breaks it apart, along with cyanide and carbon-bearing molecules that have painted many comet tails before. Visible light images should map a broad coma that grows and thins. Infrared cameras should pick up warm grains that tell us about size and mass. Ultraviolet and radio bands should trace the telltale emissions that gas cannot hide. Spectroscopy will do the heaviest lifting. Spread the light into a spectrum and the atoms and molecules identify themselves. If 3 Atlas is a natural comet with unusual seasoning, the lines will still line up with a known kitchen. They may be weaker or stronger than average. They may be oddly balanced. They should still make sense as frost in sunlight. If the usual gases refuse to present themselves at the needed strengths, the brightening must be carried by dust physics that can be checked through polarization and color. Polarization is a quiet truth teller. When light bounces off dust, the preferred direction of its electric field changes in ways that depend on grain size, shape, and coating. A stable pattern across changing viewing angles would argue for a dust population that holds its character. A swing toward normal comet values would argue that earlier measures were shaped by geometry rather than essence. Either way, the data closes a door. Astrometry is the other hinge. Measure the position of the object against background stars night after night, then fit an orbit and study the tiny leftovers. If a push is present, it should lay itself out as a small but steady deviation. A natural engine tied to rotating vents should breathe with the spin and drift with the march of the subsolar point. A cleaner thrust should keep its directions orderly, despite rotation, or compensate in a way that looks deliberate. The strength of the shove relative to distance from the sun should scale in a manner that simple models can compare. The golden survivor, near home, provides an immediate control. Around late November, it reaches its nearest point to Earth. If its spectrum remains depleted in carbon-bearing molecules, if its golden tone persists as the phase angle changes, and if its brightness curve falls in line with a slow, dust-led fade, then we learn how a carbon-poor coma behaves over time. Those lessons feed back into the puzzle of the interstellar visitor by tightening the range of what dust alone can do without strong gas support. Timelines matter. If a giant cloud exists, it expands. An expanding shell should become easier to see in some bands even while the central object dims. If a giant cloud does not exist, that absence hardens as the weeks pass and the geometry improves. In that case, the mass budget must be balanced by a mechanism that uses far less matter to make the same changes in brightness and motion. The campaign is designed to force that decision. There is a simple scoreboard to keep in mind. A broad detectable coma plus spectra that match a natural pantry plus acceleration that maps to identifiable vents means the standard comet model wins with unusual parameters. A missing or anemic coma plus spectra that refuse to show the needed gases plus a tidy and plain shove that shrugs off rotational noise means the standard model fails and an alternative has to carry the load. Either way, the clock is running, the tests are written, and the outcome will be earned in the light we collect. Begin with a fair rule. Never mistake a story you enjoy for a fact. Then, give your mind permission to model the world and see what falls out. If a craft were built to cross interstellar space and survive a swing through a bright star, what choices would a careful engineer make? Now compare those choices with the signatures we have been measuring and ask whether the rhymes are meaningful or just poetry. Durability sits first on the list. Radiation, micrometeoroids, and thermal shock punish fragile materials. A structure that skews nickel-rich would resist corrosion and hold strength across wild temperature swings. A surface that can shed heat and shrug off charged particles would age slowly in the void. A body that carries little water by mass would not be a snowball. It would be a machine with only enough volatile stock for cooling or reaction mass. That set of traits sounds like 3 Atlas, more than it sounds like a classic comet, though similarity does not equal identity. Next comes propulsion. High thrust is wasteful over years and decades. Low, thrust applied at the right moments wins the long game. Near perihelion, a tiny nudge can reshape a path by large amounts. A gentle push arranged mostly within the orbital plane makes sense when the goal is to change where and when the object will be after the swing. A vector that stays tidy rather than jittering with rotation fits that need. That picture echoes the in-plane acceleration we have seen, yet nature can draw echoes too with a lucky spin axis and a vent that dominates. Navigation sets the next constraint. A traveler that hopes to survey planets would like close looks that are not suicidal. It would also like to cross the inner system when our line of sight is poorest, so that its most sensitive maneuvers are hardest to watch. A path that threads near several worlds and places perihelion in blinding glare matches both aims. Again, the rhyme is striking. Again, we keep the brake on our imagination, because random arrivals can land on improbable alignments without secret hands to guide them. Sensing closes the loop. A probe that wants to sample dust and fields near a star might carry a sheath of particles around a core like a cocoon. It might even spit matter sunward in limited bursts if that helped manage temperature or allowed instruments to sniff a flow upstream of radiation pressure. A true sunward jet would be a strong hint for novel behavior. A geometric trick would demote it to an oddity that a rough surface can mimic. The data to separate those options is still thin. What predictions would a design traveler make that a natural snowball would not? The push vectors would keep discipline across changing season and spin, or they would vary in a way that looks like control rather than wind. The coma would remain modest even as brightness climbs, because reflection would dominate over steam-driven haze. Composition would continue to lean dry, and metal shifted beyond ordinary ranges, with a dust population that keeps its odd polarization tone across. Many viewing angles. None of those are proof. Together, they define a pattern that we can grade with fresh measurements. Now, restore the rule at the top. We do not get to crown an answer because it feels elegant. We honor the thought experiment by feeding it to the same grinder we use on every natural model. If the next spectra reveal a pantry that looks like frost and sun, if the coma swells across bands, if the acceleration flutters with rotation and traces to vents, then the design story loses, and we win a more interesting comet. If the opposite holds across independent teams and months of geometry, then the burden of proof shifts toward a stranger tale. The honest position lives between romance and refusal. Stay curious enough to frame alternatives with care. Stay strict enough to demand that every alternative write down predictions that risk being wrong. 3 Atlas has already given us a list of signatures that favor one path or the other. The coming nights will tell us which. Story can keep its promises. Stand beneath a dark sky and remember what the past weeks have done to your sense of what is possible. One traveler from deep space altered its light in a way that refuses to obey easy rules. Another traveler from our own far frontier shook off a close pass by the sun and kept a golden glow when it should have fallen quiet. They carry the same survey name by chance, perhaps, yet the human mind is not wrong to hold them together in one glance and ask what they are trying to teach. Learning begins with the scoreboard written in plain language. If the interstellar visitor grows a broad detectable coma as glare fades, if spectra show familiar gases at strengths that fit the brightening, and if the measured shove maps to identifiable vents that breathe with rotation, then the natural story holds. We will broaden comet science to include extremes that earlier catalogues did not capture. Chemistry will stretch to admit metal-rich, water-poor variants. Dynamics will absorb tidy and plane pushes that come from terrain and spin we did not anticipate. The rulebook will not break, it will lengthen. If the opposite score appears, the weight shifts. A missing or anemic coma across bands, persistent odd chemistry, and a measured push that keeps the same disciplined directions across seasons and spins will force a new conversation. That conversation will not crown an otherworldly craft by declaration. It will simply close the easy doors and leave us standing before a stranger hallway. The next steps in that hallway are obvious and sober. We would call for deeper spectra from larger telescopes, for precise polarimetry across many angles, for radar experiments if geometry allows, and for every independent team to post their methods and fits so that others can reproduce or refute. There is no bad outcome here. A natural win is not a retreat, it is an upgrade. The catalogue of small bodies would now include worlds that form or evolve in ways we have not modelled. Carbon-poor Comet would get their own family tree. Polarization that swings negative by unusual amounts would find a home in grain physics rather than in rumor. Classroom diagrams would change. The next student who points a small telescope at a faint smear of light will be meeting a richer universe. An alternative win would be heavier in the bones. It would say that intentional design may leave fingerprints in the same sky where gravity and sunlight have always ruled. That does not erase the hard work of natural science. It raises the stakes. It tells us that disciplines we built for planets and dust can also parse faint signals of guidance, control, and material choices that were not made by weather or time. The first responsibility would be caution. Extraordinary claims need a chain of measurements that strangers can break and rebuild and still get the same shape. The golden survivor near home keeps our feet on the ground, while our eyes look far. It offers a way to learn how carbon-poor Comet breathe and fade, how mineral-rich dust handles sunlight, and how survival near fierce heat depends on structure as much as on luck. Every night that amateurs and professionals record its color and brightness and texture across changing geometry narrows the space of plausible stories for the interstellar case. The two messengers do not cancel each other. They cross, calibrate. There is also a more personal lesson folded into the data. Public science is not a performance given by a few voices on a stage. It is a shared craft. When agencies go quiet because budgets hiccup, the sky stays loud for anyone willing to listen with glass and patience. When analyzers are posted with calibration steps and code, trust grows. When predictions are written down in advance, the audience becomes a collaborator rather than a spectator. That is how a mystery stops being a rumor and becomes a chapter in a textbook. So we enter the observation window with a promise to ourselves. We will not fall in love with a favored answer. We will fall in love with the process that distinguishes between answers. If the light yields a cloud and a pantry that match frost in sunlight, we will celebrate an extraordinary comet and rewrite what extraordinary means. If the light refuses to give us those signs and the small steady shove keeps writing a disciplined line, we will have the courage to follow the implications wherever they lead. Either way, these two travelers have already paid for our attention. They have made us check our categories, examine our habits, and widen our sense of what a small body in sunlight can be. Tonight they move on, quiet and relentless, while instruments cool and clocks tick toward the next clear hour. We meet them there with open eyes and clean methods, ready to learn whether the universe is serving us a rare flavor of the familiar or the first taste of something new.